Yadav, can you
hear us?
Yes, we can hear you.
Yeah, yes.
Okay, thank you.
Okay, so are you able to see the slide?
Yes,
Hello?
sir.
Okay.
Yes,
Yes,
sir.
sir.
Yes, we can see.
Okay.
எனக்கு எதுவும் தெரியும்.
Okay. Okay. So we start. Okay. So this class we look at two analytical methods to solve the constraint optimization problem. The first one is called sequential linear programming, and this is done by hand calculation. So it will be asked for the exam or second quiz. Some problem. I mean, there's no second quiz. Okay, for end semester exam, this might be asked because this is the type of problem you do by hand calculation. So successive linear programming. Okay. So the principle is that objective function and the constraints are linearized using the Taylor series at the given starting point, and the linearized function can be solved using the standard method of linear programming. Okay. Now you already studied how to solve the linear programming. So basically the method is that if you have an objective function f of x, it can be converted to linear form in the vicinity of x naught using the Taylor series. So this is actually single variable. We look at single variable objective function. So if you are given a point x naught, then the objective function can be converted to the linear approximation by this equation. So this is the linear approximation. So it is f of x naught plus first derivative at x naught into x minus x naught plus second derivative term. So we are ignoring second derivative term for the linearization. Okay. So if you have two variable objective function, then you will have x and y. So this is the approximate form of f of x y at the starting point x naught y naught. So if you know the starting point x naught y naught, so the two variable objective function can be converted to the linear form by this equation. So that is f of x naught y naught plus partial f by partial x, partial f by partial y at x naught y naught into this x minus x naught and y minus y naught. Okay. And similarly, the constraints also can be converted to the linear form. So the constraint may be a quadratic equation or cubic equation, but it can be converted to the linear form like this. And then you can solve it with the LPP methods. Okay, so let us visualize what is the meaning of linearizing an objective function. So we'll try to understand it with a simple objective function. Okay, so f of x is equal to 2x cubed minus 6x squared plus x. So this is a objective function in a single variable x, and it's a cubic equation. So let us see if you linearize it, how it will look like. So first you have to find f of x naught, then you have to find the first derivative at x naught. So f of x naught is minus 3, the first derivative of x naught is minus 5. So you substitute all these things in this equation. So f of x naught is minus 3, then f apostrophe of x naught, or first derivative of x naught is minus 5, and this is x minus x naught or x minus 1. So this is the line approximation. Okay, of cubic function. At x naught is equal to 1. Okay. So let us see how it look like. Okay. So this is the cubic curve. It goes like this. This is x not equal to 1, okay, or x equal to 1. So this is our linearized expression with the Taylor series. So you can see that if you take x not equal to 1, in the vicinity of x not equal to 1, the cubic function can be approximated by this straight line or the approximate Taylor function truncation. So this is the meaning of linearizing an objective function at a particular value. Okay, so suppose I linearize this curve at x not equal to -3. Okay, then I'll get a line like this, which is a close approximation of the curve only in the vicinity of x not equal to -3. So this is the meaning of linearization. Okay, so now that the objective function and constraints are linearized at x naught, y naught, it becomes a linear programming problem of the format minimize ax plus by equal to c plus a matrix of equality constraints plus a matrix of inequality constraint, and you can solve it using standard methods. Okay, okay. For example, you can use graphical method, and or you can use MATLAB linprobe. Okay, or you can use the Lagrange multiplier method, which you already studied. Lagrange multiplier method, which you already studied. Okay, so how to do successive linear programming? So what you studied up to now is only one step, but you will not obtain the answer in one step. Successive steps is required until you get the converged answer. So two methods are the standard method, which is easy. Then you have Frank-Wolf method, which is more difficult but accurate. Now the standard method, so at the starting point x naught, y naught, the objective function and constraints are linearized. The optima is found using standard linear programming methods. So let the optima be x star, y star. So this is taken as x1, y1. That is the starting point for the next iteration. So now the objective function and constraints are linearized at x1, y1, and the new optima is found as x2, y2. Then again, objective function is linearized at x2, y2, and the new optima is found as x3, y3, and so on. So you continue this until some sort of convergence is obtained. So how termination is obtained? So this occurs when there is no further improvement in the objective function value of f of xy. So the current objective function value minus the previous objective function value divided by the previous objective function value. We take the absolute value, and that should be less than or equal to a tolerance, say 0.001. Okay, so then you can stop the iteration. Okay, then there is something called Frank-Wolf method. This Frank-Wolf method is a improvement over the standard method. So later you will see that the standard method always gets stuck. Okay. So in the Frank-Wolf method, the previous optima is not directly used as the next starting point. So what you have to do is that first linearize objective function and constraints at x naught, y naught, and obtain the optima x star, y star. So now x1, y1 is obtained by a line search between x naught, y naught, and x star, y star. So x star, y star is here, x naught, y naught is there. You have to write the parametric equation of the line joining x star, y star, and x naught, y naught, and you have to find h star. Okay, so x1 by x, okay, h star, and that will give x1, y. Okay. So x1, y between x naught, y naught, and x star, y star in the original objective function, not the linearized objective function. Because linearized objective function is too rough or too approximate. Okay. So then this is the starting point of the next iteration. So this x1, y1 is the starting point of the next iteration. Okay. So minimize this objective function using sequential linear programming method. So one complicated objective function is given. Okay, for exam, this type of functions will not be asked. Some more simpler functions will be asked, like some quadratic equation or cubic equation. Okay, so this is taken from some textbook. Okay, subject to some constraint, x is greater than 0, y is less than 24, and y is greater than or equal to x. And starting point is given, that is 210. So here all the constraints are linear constraints. Okay, so there is no non-linear constraints. Okay, so write the constraints in the standard form. X is greater than 0. 64 minus y is greater than or equal to 0. Y minus x is greater than or equal to 0. So this is this, and this is this. This is in the standard form, and we are writing in the form greater than or equal to 0. But if you use the MATLAB linprog, then it has to be written in the less than or equal to 0 form. Okay. So these constraints are already linear, so no need to linearize this constraints. So only this objective function must be linearized at 210. Okay, x naught y naught equal to 210, so it must be linearized at 210. Okay, so linearize the objective function at 210. So f of x naught y naught is 4.75, and partial f by partial x at x naught y naught is this value minus 0.03. Partial f by partial y at x naught y naught is minus 0.002. Okay, and then okay, so you need these values. Okay, you can substitute those values here. F of x naught y naught is 4.75. Then this partial f by partial x at x naught y naught is this value. Partial f by partial y at x naught y naught is this value. So x naught is minus 2, y naught is minus 2. So this is the linearized representation of objective function at 210. Okay, so linear objective function and linear constraints. So you can solve this linear programming problem. Okay, so linear programming problem is written like this. So with the graphical method or slack variable method, that is Lagrange method, you can solve it. Obviously, in the exam, you cannot use the MATLAB toolbox. So you have to use some method like this. So the answer is x star y star is 64, 64. So now check the violations of the original constraints at 64, 64. Original constraints means non-linearized constraints. Okay. Anyway, in these constraints, we are not linearizing them. So check the violations of the original constraints at 64, 64. So constraints are not violated in this iteration. So we can go to next iteration. The next iteration is that you have to linearize the objective function and constraints at x1, y1 is equal to 64, 64. Okay. Okay, then, okay, in certain cases, there may be some constraint violation in an iteration. If the violation is large, you may have to restart it with a new starting point. If the violation is small and within a given okay, so now let us go to next step. So x1, y1 is equal to 64, 64. So again, you have to linearize the objective function and constraints at x1, y1 equal to 64, 64. So f of x1, y1 is 18. Then partial f by partial x and partial f by partial y is equal to these values. Okay. So you get this objective function like this. So you can see that this y, partial f by partial y becomes 0. So this term vanishes. The y term vanishes. So minimize this objective function. Actually, it has only x. Okay. So you can write plus 0 into y. Okay. Plus 0 into y, subject to the already linear constraints, G1, G2, and G3. So so when we solve this, we don't find a solution which satisfies the constraints. In fact, the solutions we get will not satisfy the constraint. So in this case, the algorithm will get stuck in the second iteration. So in this iteration, it will get stuck. Okay. So the remedy is that you have to restart this entire problem with a new starting point. And hopefully it will converge to the solution. Okay, so now if you were to use the Frank-Wolf method, the situation is different. Okay, so we find x1, y1 by conducting a line search between this 210 and 6464. Okay, so you have to obtain parametric equation of the line joining 210 and 6464. So this is the parametric equation of the line joining 210 and 6464. And this has to be substituted in the original objective function and minimized. Okay. So you may need Cauchy method or Newton's method. Okay, so the answer is you get H star is 0.027 and x1, y1 is 3.694 and 11.475. So next we have to linearize the objective function at x1, y1. That is at this value. Okay, not at 6464. It has to be linearized at this value. 3.694 and 11.475. Okay, and we find the optima x star, y star, and then x2, y2 is found by again doing line search between this x1, y1 and x star, y star. Okay. So example 2 is a problem with non-linear constraints. So in our previous problem, all our constraints were linear. So there is no need to linearize the constraints. Only objective function need to be linearized. But in this example, both objective function and constraints have to be linearized. Okay, so objective function is like this. And this is the non-linear constraint. Okay, it is a quadratic equation in x and y. Then there is a linear constraint. Okay, so let us see only the first step of how this will be solved. Okay, so first the objective function has to be linearized at 0, 0. Okay, so 0, 0, f of x naught, y naught is 170. Then you have to substitute all these things. And finally, you get a simplified answer. So this is the linearized objective function at 0, 0. This has to be linearized because it is non-linear. Okay, so you have to find this G1 at x naught, y naught, partial G1 by partial x at x naught, y naught, partial G1 by partial y at x naught, y naught. So if you substitute everything, you get 1 plus 10x is greater than or equal to 0. Okay, so that is the linearized representation of this. Okay, linearized representation of this. Okay, then G2 is already linear, so there's no need to linearize it. You just rearrange the x and y terms so it matches this. Okay. Okay, so now you get the linear programming problem. So this is the linear objective function. These are all linear constraints. Linear constraints. So we can solve it graphically or with Lagrange method or with the MATLAB LinProg routine. So in any case, the answer is x star, y star is 0, 20. So we started with 0, 0. And now we got 0, 20. The next step, as per Frank-Wolf method, is to draw the line, do the line search on the line joining 0, 0 and 0, 20. And on that line, you have to find H star, and that will give X1, Y1. Okay, so that is done here. So this is the equation of the parametric equation of the line joining, 0, 0, no, 0, 0 and 0, 20. Okay. So X will be 0 and Y equal to 20H. Y equal to 20H, X is equal to 0. Okay, so you have to substitute these values in the original objective function. So what is the original objective function? This is the original objective function. Okay, so in the original objective function, wherever you see X, you put X equal to 0. Wherever you see Y, you put 20H. And if you do the minimization, you get the answer is X1 equal to 0 and Y1 equal to 2.898. Okay, so this is the starting point of linearizing the next iteration. So next, in the next step, the objective function and constraints must be linearized at this at X equal to 0 and Y equal to 2.898. But before you do that, you have to check that the original constraints G1, G2 are not violated at X1, Y1. Okay, so it is found that G1 is violated. Okay, so it means that you have to restart with a new starting point, or xy equal to 0, 0 is not a good starting point. You have to restart with a new starting point. So you can see that this sequential linear programming is not a good method because it is too approximate. So when you linearize a complex objective function, it will lose all the important information. Okay, so sequential linear programming is not a very good method. It's difficult to convert. Okay, then there's something called sequential quadratic programming, which is an improvement over sequential linear programming. So that is more widely used. So the method is similar to sequential linear programming approach. The only difference is that objective function is approximated to quadratic form, and the constraints are approximated to linear form. So then you do the same thing. You repeatedly convert to quadratic form and find X1, Y1 till convergence of those. Okay, so the objective function is approximated at X0 to the quadratic form, or using up to second derivative terms of the Taylor series. So in the last slide, we used the terms up to this for the linearization. But for converting to quadratic form, you have to add this second derivative term for the Taylor series approximation. So now you get the quadratic approximation. So this is for single variable. So only X is there. Okay. Okay, now for two variable objective function, the quadratic form becomes like this. So two variable means X and Y will be there. The starting point will be X0, Y0. So f of X0, Y0. Okay, then partial f by partial x at X0, Y0. Partial f by partial y at X0, Y0. You have to know this. And then you need to find this Hessian matrix, or del squared of, or second derivative of objective function matrix. So del squared f at X0, Y0 also has to be known. So this is the Taylor series truncation up to the second derivative. Okay, then another important thing is that if you are doing the hand calculation, it is extremely difficult to pre-multiply and post-multiply with x minus x naught because so many terms will come. So what is done is that instead of x minus x naught, we put d1, y minus y naught, we put d2. So now everything is simplified. And later in the end, you can replace d1 with x minus x naught and d2 is y minus y naught. So the difficult part is done using d1 and d2 only. Okay, and then another important thing is that in the objective function, you can ignore this constant term. So the constant term will not affect the minimum. Okay, it's the same for the sequential linear programming also. So you can neglect the constant term in the objective function for minimization. So, so this you can ignore because it will make the hand calculation more easy if you remove the constant term. Okay, so final quadratic form starts from here to here. Okay. So this is the first. Okay, and this is the second derivative form. Then the constraints are converted to linear form. The constraints are not converted to quadratic form because then it will become more difficult. Okay. So why it is converted only to linear form? Okay, so why the objective function is converted to quadratic form and constraints are converted to linear form? The answer is that it is simpler to solve it in this method. So if the objective function is quadratic and the constraints are linear, then it is easy to solve the using the simplex method for quadratic problem. So let us see what is simplex method for quadratic problem. So I have graphically illustrated it. Okay, so here you can see that the constraints are linear like this. Okay, and they may form a polygonal region, a convex region, and the objective function is quadratic. So the objective function will touch the line between two vertices. Okay, so that is a special property of this simplex method for quadratic problems. Okay, so how do you solve this problem in the computational method? So what you have to do is that you have to find vertices of this polygon and you have to do line search between all these vertices. Okay, line search between all these vertices and the contours will hit the one of these lines. Okay, so sometimes contour may come like this, it may hit here. Sometimes contour may come like this, and it may hit here. So this is relatively straightforward and easy to implement as a computer program. So that is why objective function is kept quadratic and constraints are kept linear because you can use this method. Okay, then procedure for basic sequential quadratic programming. So first, a local starting point x0, y0 has to be selected inside the feasible region. Okay, and the objective function and constraints. Objective function is converted to quadratic approximation, and constraints are converted to linear approximation. Okay, and it can be written in terms of d for ease of hand calculation. Then solve this local optimization problem and find d1 star and d2 star. Okay, then you can recover x1 and y1 once you get d1 star and d2 star. So d1 star plus x0 is the x1 and d1 star plus y0 is the y1. Okay, so then again obtain the local quadratic approximation at x1 y1. Okay, x1 y1, and again solve for d1 star d2 star and then get x2 y2. So these iterations are repeated until convergence criteria is satisfied. Okay, so one example. So using sequential quadratic program, solve this a nonlinear optimization problem. So you can see that objective function is nonlinear, constraint is nonlinear. I mean, one constraint is nonlinear, and this constraint is linear. Okay, so only one constraint has to be converted to the linear form. The starting point is given 2, 1. So show the first iteration in detail. So usually for exam, you have to do only one iteration. So the method is use the D1, D2 form for ease of hand calculation. So x minus 2 is represented by D1, y minus 1 is represented by D2. Then you have to find the second derivative matrix at x0, y0. So second derivative matrix at x0, y0 or the 2, 1 is obtained like this. So second derivative matrix is obtained. Okay, then you have to find first derivative matrix also at 2, 1. So that will be 23 by 4 and minus 47 by 4. So now quadratic form of the objective function is written in the terms of D1, D2. Okay. And if you simplify this, simplify or expand this, then you get the quadratic approximation of the objective function. Okay, at 2, 1. So you can see that there are quadratic terms. D1 is quadratic, D2 is quadratic, then D1, D2 is there. Then D1 and D2 separately are. So next is constraints have to be converted to linear form. So this is actually non-linear. Okay. So f of xy is equal to 0 and del f, that is xy at 2, 1 is 1, 2. Okay. So substitute this value 0. This is 1, 2, and you have to use the D1, D2 notation. Only then it will match with the objective function notation. So this is the linearized expression of xy minus 2 is equal to 0. Okay, then there's another objective function, x plus y minus 1 is greater than 0. It is already linear, so there's no need to linearize it. But there is a problem because this is written in terms of x and y, and all these are written in terms of D1 and D2. Okay, so if you put x is equal to D1 plus 2, y is equal to D2 plus 1, okay, then this will be converted to D1, D2. Okay. So two constraints are there, 1 and this is 2. I mean, two linearized constraints are there. This is number 1 and this is number 2. Okay, so now we get the quadratic programming problem. The objective function is quadratic and constraints are linear. Okay, so this can be actually solved with some MATLAB routines. Okay, we can use some MATLAB routines and immediately get the answer. But for exam, you have to use some graphical method or some manual method. So if you want to solve this manually, what you can do is that you can put D1 equal to minus 2 D2 and substitute it here, and you will get a single variable objective function, and you can solve it with a golden section method or something. Okay, so you will get D1 star and D2 star at the end of it. So D1 star is minus 0.921, D2 star is 0.461, and that is okay. So this D1 star is converted to x1, D2 star is converted to y1 using these relationships. Okay, so x1, y1 is got, which is the next iteration point. So what you do is that so first you can see that before you do the next quadratic approximation, you have to see that these two values don't violate the constraints. Only then you can do the next iteration. Okay, so let us check the if x1, y1 is a good value. So, but if you substitute x1, y1, you can see that f of x1, y1 has improved. Okay, because f of x0, y0 was 12.25. F of x1, y1 has become 5.688. So, objective function value has improved. Okay, then the constraint violation of equality constraints. Actually, we expect this to be 0, but we are getting minus 0.423, which is a small violation. And then G of x1, y1 is 1.539x, which is greater than 0, so there is no violation. Okay, so this is acceptable for next generation. Okay, so we'll briefly see. So next generation, actually we are not asked to do next generation. This is just for illustration. So next generation at x1, y1. So you have to find this f of x1, y1. I mean partial f by partial x at f1, y1. X1, y1, partial f by partial y at x1, y1. And this is the del squared of at x1, y1. X1, y1. Okay. So if you simplify this, okay, then you have to linearize the first objective function. You will get like this. The second objective function has to be rewritten in the forms of d1, d2. So if you solve this problem, so you will get an answer that x2, y2 is 1.04 and 1.89. Okay, so let us check the improvement at x2, y2. You can see that objective function value has reduced to 5.044, and whereas the previous iteration it was 5.688, then equality constraint violation has become less. Now it is only 0.013, and the inequality constraint value is still positive. That is 1.943. Okay. Then in the next iteration, okay, you get, x3, y3 is equal to 1.001 and 1.99. So you can check the objective function value and the constraint violation. So things are improved. Okay, so, okay, so finally, after some more iterations, the convergence is obtained. Convergence is obtained, and this is on the right track. So we are going on the right track because successively we are getting improved values of the objective function. Okay, we can stop here. Stop.